Hello all, welcome to another video of the regression analysis course. In this video, I'm going to talk about the differences between variance and an interval estimator of average value of y given x naught and an individual value of y given some point x naught. Let's begin with the simple linear model. yi is equals to beta naught plus beta 1 xi plus epsilon I, where yi is the dependent variable, xi is the independent variable, beta naught and beta 1 are model parameters, and epsilon I is the error term. We make some assumptions on error terms such as expectation of epsilon I is 0, variance of each epsilon I is sigma square, all EIs are IID and have normal distribution. When we make these assumptions on error term, we get simple linear regression model, which is that the mean of the dependent variable is a function of independent variable. That is, expected value of yi is equals to beta naught plus beta 1 xi. And we have seen estimates of both these values. We know the estimate of expected value of yi given x naught, and we also know an estimate of yi given some point x naught. An estimate of expected value of y given x naught is equals to beta naught hat plus beta 1 hat x naught, where we are trying to estimate the average for all individuals who have the same value of x naught. And an estimate of y for some value of x naught is equals to beta naught hat plus beta 1 hat x naught. But here we are trying to predict the outcome of one specific individual with x naught. Then what is the difference between these estimates? Let's try to understand it with an example. Say we have this data set where we have exam score of some students and their corresponding study hours. So we have some student who studies for 4 hours and have exam score 65. Another student who studies for 3 hours and ended up scoring 68 points, and so on. And now we have a question. On average, how do students who study 8 hours perform? So in this problem, we are trying to find the average score of all those students who studies for 8 hours. Now imagine a student comes up to you and tells you that they study for 8 hours and asks you that how much approximately would they score. In this case, you would find an individual value of y given x naught. But here's the thing, given same value of x naught, both the estimates will give you the same answer. But if you look at the questions, both the questions are different. The first question asks you that here's the data set. Now you look at the data set and tell us all the students who studied for 8 hours, what would be their average score? But in the second question, you are trying to find the score of a single student who studied for 8 hours. And given x naught is equals to 8, the estimates for both the problem is beta naught hat plus beta 1 hat times 8. But let me tell you all something interesting. The second problem, which is the predicted value of individual value of y, is bit more uncertain. And now let's try to see why is the second estimate, that is an estimate of individual value of y, more uncertain. Imagine two students walk up to you and tell you that they both studied for 8 hours. Now tell me, will they necessarily get the same score? Probably not. But the question is why? Because even if they both studied for the same amount of time, there are other factors that might affect their exam score, such as test anxiety or understanding of the material. All of these other factors can affect their exam performance. So when we estimate an individual value of y for some given point of x naught, we are actually acknowledging that there is some randomness or variation present there. And what is that term that takes care of this randomness? The error term takes care of this randomness present in the model. So when we are talking about an estimate of an value of y for some given point of x naught, we are taking the error term into the account. And therefore, when we consider the simple linear regression model, that is expected value of y for some point x naught, which is beta naught plus beta 1 x naught, here its estimate is equals to beta naught hat plus beta 1 hat x naught. And in this estimate, the only source of uncertainty we have is because of the regression coefficients beta naught and beta 1. The only uncertainty we have in the model is because we do not have an accurate and exact value of beta naught and beta 1. Therefore, variance of this estimate at point x naught would be equals to sigma square times 1 divided by n plus x naught minus x bar whole square divided by sxx. And this variance we have is because we do not have an exact value of beta naught and beta 1. We have uncertainty due to model estimates. And now let's look at the linear model, that is y at some point x naught. Here it is equals to beta naught plus beta 1 x naught plus epsilon naught. And its estimate is equals to beta naught hat plus beta 1 hat x naught. But in this estimate, we have variability due to the estimation of regression coefficients because we do not have an exact value of beta naught and beta 1, and also because we have error term in this simple linear model. So in this estimate, we have uncertainty due to model estimates beta naught and beta 1, and also the randomness in individual responses. And therefore, the variance of an estimate of y at point x naught is equals to sigma square times 1 divided by n plus x naught minus x bar whole square divided by sxx, which is the variance we have due to model estimates, plus sigma square, the variance we have because of the error term. And we have proved that yes, it is equals to sigma square times 1 plus 1 divided by n plus x bar minus x naught whole square divided by sxx. And from here, we have that the variance of an individual value of y at some point x naught is greater than the variance of an estimate of average value of y for some point x naught. Because when we talk about an estimate of y for some point x naught, there we have uncertainty due to model estimates. Whereas when we talk about an estimate of y at some point x naught, we have uncertainty due to model estimates and the error term present in the model. Perfect. And now let's talk about the interval estimator of these estimates. When we talk about an interval estimator of average value of y, we call it confidence interval of expected value of y given x naught. And we have seen that the confidence interval is beta naught hat plus beta 1 hat x naught minus the critical point times the standard error of that estimate, comma beta naught hat plus beta 1 hat x naught plus critical point times the standard error of the estimate. If you look at the confidence interval of this expected value of y given x naught, we have an estimate of expected value of y for some point x naught minus the critical point times the square root variance of that estimate. And the upper limit is an estimate of expected value of y at point x naught plus critical point times the square root variance of that estimate. And an interval estimate of response, also known as the prediction interval of individual value of y at x naught, is given by beta naught hat plus beta 1 hat x naught minus the critical point times the standard error of individual value of y at point x naught. So the difference between an interval estimator of mean response and an interval estimator of individual value of the response is that in the confidence interval of average value, we use the variance of the estimator of average value of y. Whereas in prediction interval, we use the variance of an individual value of y at some point x naught. And variances of both these estimates are different. That makes the interval estimator of both these estimates different. So, in the confidence interval, we use the variance of the estimated mean response, which is expected value of y given x naught hat. Whereas in the prediction interval, we use the variance of the predicted individual response, that is y at point x naught hat. And we know that variance of y hat x naught is greater than the variance of estimated mean response, because that includes two sources of variability: the variability from estimating the regression coefficients and also the inherent random variation in individual outcomes. In contrast, the variance of expected value of y given x naught hat only has uncertainty due to the regression coefficient. And statistically, we say that this is the reason why prediction intervals are always wider than the confidence intervals, as they account for more sources of variation. But everything has a mathematical proof. So let's try to look at the mathematical proof of why is the prediction interval wider than the confidence interval. Given any interval a comma b, the length of an interval is given by upper limit minus lower limit. When we have interval a comma b, the length of this interval would be equals to b minus a. We know the confidence interval for expected value of y for given point x naught, which is this. Now, if we try to find the width of this interval, the length of this interval, it would be equals to the upper limit of the confidence interval minus the lower limit of the confidence interval, which is equals to the upper limit, which is beta naught hat, plus beta 1 hat x naught plus the critical point times the variance minus beta naught hat minus beta 1 hat x naught plus t critical point times the square root variance. And if we try to simplify it, we get twice the critical point times the standard error. And if we try to look at the length of the prediction interval, the length of the prediction interval would be its upper limit minus its lower limit. The upper limit of the prediction interval is equals to beta naught hat plus beta 1 hat x naught plus critical point times the standard error. And the lower limit is beta naught hat plus beta 1 hat x naught minus critical point times the standard error. And if we subtract this lower limit from the upper limit, we get 2 times the critical point times the standard error of an estimate of y at point x naught. So now let's try to see which interval has greater length. The length of the prediction interval is this, and the length of the confidence is twice the critical point times the standard error of an estimate of mean of y at point x naught. Clearly, if we look at the standard error of y at point x naught, it is greater than the standard error of an estimate of mean of y at point x naught, because in the standard error of the individual value of y, we have uncertainty due to model estimates and also uncertainty due to error terms. So we have an sigma square hat times 1 plus divided by 1 plus x naught minus x bar whole square divided by sxx. If we multiply 2 times the critical point both sides, we have length of the prediction interval on the left hand side and we have length of confidence interval on the right hand side. And therefore, we have the mathematical proof that the length of prediction interval is greater than length of confidence interval. And thus, we have the proof that the prediction interval is always wider than the confidence interval.